Good evening, everyone. You may have heard my earlier comments. Hargrave is unable to join us tonight, but he will be with us later in the year. He sends his apologies and is looking forward to meeting us all. Next week, we've got our dear friend Whit Reeves addressing us, and he's going to talk about some observations he made, VLF observations he made during the solar eclipse of, when was it? October last year. But this evening, Wolfgang was already lined up to share with us an update and some new observations that he had published, and he's been moved to the top slot, as it were, this evening. It's always good to have you with us, Wolfgang. Wolfgang has set a very high bar in conference organising as far as the European Conference on Amateur Radio Astronomy is concerned. And we're going to try and meet that high bar in the UK. So please register your interest on the website. I'll put the address up at the end. Because it's the first time this European conference has been to the UK, we have no idea if we're going to have 50 people or 150. And it won't be until September next year, but so we've got plenty of time. But as we all know, time flashes by at an alarming rate. So we're hoping to put on a really good conference. So if anybody's got any ideas, do let us know. Andrew Thomas and I are going to do our very best to pull this together in a competent fashion. As the example has been already set to us.
Better still, if you want to do something, let us know. Some of you on this call have already volunteered, which is great, and thank you very much.
Yeah, you're absolutely right. Yeah, we've got 36 people so far say they're intending to attend, and the press release only went out this month. And we've already got the beginnings of a local organising committee. So it's looking good. But the business this evening, Wolfgang, we're always pleased to have you with us because you operate in the amateur sphere along with the professionals. And I've said this before, and I have I make no apologies for saying this again. It was Wolfgang very early on in my amateur radio astronomy career asked the question, why do we do it? And he answered his own question by saying, because it's fun. And I just found that so inspirational. And Wolfgang, I've quoted you so many times. Anyway, our monitors are yours this evening for as long as you wish. Over to you, sir.
Thank you very much. Thank you very much for the introduction. And I want to share some of the fun tonight. I have to apologize that I didn't plan to give the main talk this evening. I had planned to give something like a 10 minutes brief overview of the latest FRB observations that we are doing. So it will be a relatively short presentation that I will be giving. I've expanded that a bit, looking a bit back in the history. So it was just a quick preparation. My apologies for that. So let me share my screen. So hopefully that's coming up, and I need to get that full screen. So I hope everybody's seeing it full screen now. Okay, what I'm intending to talk about is once again about fast radio burst observations that we are doing at our observatory. And I gave a presentation, I think about 2 years ago, when we had done our first experiments, our first observations. And that's actually what I would like to start with, picking up from there. We had a first observation campaign. It was related to the FRB, which has the name 2020-11-24A, which is the date of the first occurrence of this FRB. And the triggering point at the time for us, we never did try any FRB observations of any seriousness, but the triggering point was a astronomer's telegram from the CHIME FRB collaboration. And that was kind of interesting because it showed that there might be a chance for us to observe something. So we started observing. And actually, it took a while. We had about 90 hours of observation time with nothing in there. But then, indeed, we had our first FRB, and that was a very, very strong one. It was on the 15th of April in 2021. You see the detection plot here. It's a so-called waterfall diagram where on top you have the pulse itself, so it's intensity over time. And then you see the intensity depicted by the color in this graph here. And this shows the intensity over the frequency. So we're observing with 100 megahertz of bandwidth from 1330 to 1430. And there you can see that the pulse is broadband, so it occurs at essentially all of the frequencies. What you do see is that there's quite some variation, which is the effect of scintillation, something that's also known from pulsars. So this was our first observation. We were extremely proud of it, and we also submitted a astronomer's telegram because this was an extremely bright pulse. And as a result of that, that triggered a cooperation with other people, with other organizations that were observing this FRB, or that organization that did do FRB work with similar size dishes. And this cooperation was with the Westerbork telescope in the Netherlands, which is also a series of 25-meter dishes. The Onsala telescope in Sweden, which is yet another 25-meter dish. And the Torun Observatory, that is a 30-meter dish in Poland. So we came in contact with that. The triggering point was our own observations, and we started cooperating on this. And what we did was we ran an extended observation campaign, which is depicted here, and I have to explain that a bit. Each line like this is an observation. Over time, you can see it's running from essentially April, March of 2021. And then this first round was until January of 2022. So each of these vertical lines is an observation. And it is in the vertical, it's shown at which frequency it was done. So this is our 100 megahertz, and these are all our observations. And you can see that we can actually, if we go for it, implement a very large amount of observations, long observation times. As you can see, there were other observations by the Westerbork telescope at lower frequencies, but also in the L band, like here. Torun has the capability of working in S-band, so there were some S-band observations. And the Onsala observations are the green ones, also in L-band. So this was the observation. You see, we stopped here, and that was a time when we did some upgrading and maintenance on our telescope. We replaced the low noise amplifiers with new ones, better ones that we got. So that took some time. And this is the second part of the observation, which runs from January 22 to essentially March 22. Again, we could only start in the February timeframe. So this is where we observed again. As you also can see, the times when a observation of a pulse was made, this is a dotted black line. So these are all events that were observed. You can see that there was a very active phase of this FRB, then it became sort of silent, then there was a little bit, and then it picked up in early 22 again. So this is essentially the observation campaign that we did jointly with the other telescopes. Now, what is the summary? Our observing effort on this FRB were around 1,400 hours of observation time. If you take all telescopes together, we had 3,500 hours of observation time. We ourselves had 16 birds, which we detected during this time. So there are not that many. If you think about 1,500 hours and then you have 16 bursts only. If we take the other telescopes into the equation, we had a total of 46. Of course, it took quite some time to work through all the data and to find out what are the conclusions that we can draw from that. And all the conclusions are explained in detail in a paper which is published in Nature Astronomy. I give the reference here. That was published early January this year. And there are essentially two findings. Of course, a lot of things which are in this paper. It's a fairly long paper and lots of things in there, but it really are two main things. First of all, I should mention that all these telescopes in that size range, 25 meter, what we are seeing is only the tip of the iceberg. So we are seeing the very bright pulses. We don't see the smaller, the less energetic pulses. These are observed by bigger telescopes and telescopes like Effelsberg and the Chinese, the big one, the FAST telescope. And there were publications from these observations from the big telescopes, and they showed what is the burst rate at which energy. So how does the burst rate drop with higher energies? What these big telescopes cannot do, they cannot do very long observation time. So they're missing, by the nature of the beast, they're missing the very bright ones. Eventually they capture one, but that's not, that is not something that they can deliver. What is the rate of the very high energy pulses? And that's where we come in, and our colleagues at the other telescopes. And what we found was that you have a higher burst rate of the higher energy pulses than you would expect from the extrapolation of the low energy pulses. So it's sort of a break in the distribution, which is kind of interesting. And you just have, first of all, you have to take it as a fact, as an observational fact. Then there was a second finding, which in a way is a bit speculative. What we did is we looked at the distribution of the non-repeaters. Of course, it's not, these are different FRBs, so it's a little bit speculative. How do you develop a distribution of the energy from that? But once you know the distance, you can make an estimate of the distance. And what we found is that the energy distribution of these non-repeaters, so these many non-repeaters that have been observed, are fairly similar, with a similar break in the energy distribution. So the suggestion there is, of course, that's not a hard finding, but a suggestion that these are actually the same thing. So there's a link between what we say, a link between the repeating and the non-repeating fast radio burst, because that's one of the discussions that you have. Are repeating fast radio burst and the non-repeaters, are they actually the same thing? And the non-repeaters are just characterized by the fact that you haven't looked long enough. So that's what we are suggesting as part of this observation campaign. Okay, this is our first effort in FRB observation, which turned out to be reasonably successful. And of course, then you look what other things are around, what are other options. And then we had, again, a trigger by the CHIME telescope. I should mention that the CHIME is really very good at detecting FRBs. So they scan a large part of the sky. So they detect a lot because they're looking at a big part of the sky at the same time. And they sent out an astronomer's telegram with a title 9 burst in 3 days from the newly discovered repeating source of fast radio burst. So this is again a trigger. We again found that given on the intensities that CHIME was seeing, that we might have a fair chance of looking at it. So we have been observing that source, and we ourselves so far have more than 1,000 hours of observation time, and plus what the other telescopes are contributing. And we're still active on that observation. We have detected 101 pulses so far. If we take the other telescopes as well, that's 191. So a fairly large population of pulses, or these high energy pulses that are detectable by 25 meter class dishes. Again, we had a very episodic behavior. We started immediately after the publication of the astronomer's telegram. And the first 83 pulses of the 100 we had during the first 40 days. So there was really a concentration. It has very much decayed, but still we do see something. The very last pulse that we have seen was this year in January. Of course, the evaluation of all that data is still ongoing, probably a couple of months before we are ready to publish something. But as a very first finding, we can say the characteristics very much resemble that of the other FRB, of the FRB 2020. So again, we see the break in the pulse energy distribution. And it looks like we can even say that with more confidence now. And there are some other things that we have still have to look into as far as the energy distribution is concerned. So there seems to be a fairly similar distribution that we are seeing. And as we have much more pulses, the statistics is much more relevant. So this, I can't say very much more at this point in time about it, as we are still working on evaluating all the data. And so we have to see what science conclusions we can draw from that. In the meantime, we will continue observing that, unless, and which is actually the case, we are looking at yet another FRB. And this is our third one. Again, same story. We had an astronomer's telegram from CHIME, which did the first detection. That astronomer's telegram was published on the 26th of January, and it was detected on the 14th of January this year. And yeah, again, that's the title of the astronomer's telegram, CHIME FRB discovery of a new repeating fast radio burst source, FRB 2024-0114A. We started observation on the 31st of January, and the first 100 hours of observation, we had none, nothing, we saw nothing. But then in the next 100 hours, and that's pretty much until today, we had 5 detections. So in the second 100 hours, we had 5 detections, and number 5 or 5th was just yesterday. And we are at the moment, this is our main observation effort. If you look at the number of pulses in which time, this one is sort of in between. The first one were 1,400 hours, 16 pulses. Now we have 200 hours and 5 pulses, and the most active one was the one I just talked about. So this is our main effort at the moment. And here are the detection plots of the first detection. To explain that a bit, these are actually 2 separate plots, but I've put them on one page. This is what we typically get as a first result, which is, in this case, of course, the pulse itself. Then one of the things that we look for, or to be more precise, we don't look for that by eye. We have an automated artificial intelligence supported analysis tool, which looks essentially at this picture. And this is a so-called bow tie diagram. And what that shows is the intensity, of course, over time. And the vertical is the dispersion. So what you will get if it is a broadband signal at a specific dispersion measure, you will see a dot in the middle, and then it's sort of, and that's sort of spreading out. Because it's not a very good signal to noise ratio, you cannot clearly see it, but yeah. One of the characteristics also of a fast radio burst is that they are fairly broadband. And it's not very well to be seen here, probably, that there's a vertical line, which means it's all of the frequencies. So therefore, I have done yet another plot where I do a band pass equalization. Then it's easier to see that essentially the signal is seen at essentially all of the band, with maybe a bit of exception here. Due to scintillation, it also varies in intensity. It's not a very strong signal, but anyway, it's a clear detection. Yeah, this is the first. We have 4 more about the same signal to noise ratio that we have detected so far. What do we know at this point in time about this FRB? First of all, it was originally detected by CHIME, but then there are many, many other telescopes that I'm aware of. We have also done observations and positive detections, of course, ourselves, our cooperation partners in Västerborg, and also our cooperation partners at Torun in Sweden. There are detections in Effelsberg from the Nauset telescope in France, the Parkes in Australia, the Chinese big one, FAST, and the Northern Cross in Italy, and the GMRT in India. And there may be others that I'm not aware of. I only know the ones that have published in Astronomer's Telegram and those where I'm in direct contact with the scientists on site. There is a tentative localization, and the putative host galaxy is within a galaxy cluster, which is at a distance of 425 megaparsec. So a bit like the order of 1.3, 1.4 billion light years. The other two, by the way, they're a bit closer by. They're about 1 billion light years, but I mean, it's quite a distance. So the signal, if you think about it, it travels for about a billion years before it hits our telescope. What is presently ongoing is a evaluation of a interferometry observation, which hopefully will further refine the position so that we can maybe bring it down to a single galaxy, not a total galaxy cluster, or at least confirm the original localization. We're hoping to get something in the micro arcsecond resolution. I have to say this interferometry experiment, this VLBI experiment, is not something that we're involved in because we don't have the capability as far as our timing accuracy is concerned. So we're out of that loop, but we're in the loop in the sense that we are informed and we know what's going on. So we keep our fingers crossed that we get good data out of that observation. And we'll see. At the moment, this FRB is the one where we have the highest priority as far as observation is concerned. We put the other one a bit in the background. We are using all the observation time that we can realize on this FRB. Okay, I would like to finish tonight with another fast radio burst, which was recently detected, and we have not observed it. And we have no intention to try it, but I find it so interesting that I would like to introduce to that. This is a detection which was reported just a few days ago, I think, by ASCAP in an astronomer's telegram again. And what they reported is that they had a FRB detection, and these were 5 bursts. It's a repeating FRB with 5 bursts, and these 5 bursts occurred within 1 minute on the 16th of February. And I have to say, we have one occasion in our most active FRB where we had 2 pulses separated by only 12 seconds, but 5 bursts in 1 minute is really something. Of course, the first thing that you look at is there a periodicity in that? But unfortunately, it's not. It's I mean, it's a whole story over and over again that nobody sees any periodicity in the pulses. And of course, such a short time frame and 5 bursts would be a very good candidate for seeing periodicity, but there is none. The interesting thing about that is that ASCAP did observe the same field since the beginning of February, again and again, for some tests and for other purposes. They have collected 13 hours of observation time in that time frame. So in that time from the 1st of February until the 16th of February. And they only had that detection in this 1 minute. All the other times there was none. And what's even more supporting that this is a very short appearance of a repeat fast radio burst is a follow-up observation by FAST telescope, the big 500-meter dish in China. They did it on the 22nd of February for 1 hour, and they didn't see anything. And I should mention that because of the very large collecting area of the FAST telescope, they typically see a lot. I mean, for the sources where we see a pulse every now and then, every 2 or 3 days, they see something like a couple of tens in an hour or even more. All fainter, but they do see it. But they did not have any detection down to their detection limit on this FRB. So I find this very interesting. First of all, we know that fast radio bursts, the repeat fast radio bursts, are episodic. So they are more active, and then there are times when they're less active, then they may come again, and so on. So that's typically a matter of weeks or months of activity and then silence, and then maybe come up again for a certain period. If you let me skip back to that, which you can see there's an activity phase, then a small activity phase, and then again an activity phase here. But this is coming back to this one. This is a very short activity phase, very interesting. We have not made an attempt to look at that location, first of all, because it's probably gone. And at the moment, we are concentrating on this other FRB. Otherwise, if we had ample of time, we would try it. But I just wanted to show that to you. It's not something that we have detected or that we are observing, but I find this really, really interesting that there is an activity phase which covers only a minute. All right, I guess, as I said, it's going to be a short talk because I had it planned differently. Just a 10 minutes thing that I was intending to do. So this is all I can tell you at the moment, and I'm ready for any questions.
Yeah, thank you very much, Wolfgang. Yeah, that was very interesting. I can't remember, but when you're doing your observations, do you have to have operators on site, or can you work remotely?
We have to have operators on site for safety reasons. Yeah. Technically, we can operate the instrument remote. but our rules are there has to be an operator on site all the time. So it's 100, if we talk about 1,000 hours or 2,000 hours, that's 2,000 hours somebody sitting in the control room.
That's quite impressive. And are there any more clues as to the mechanisms that cause these bursts? I know when you've spoken before and when other academics have spoken, it seems to be a subject of discussion, but nowhere near any conclusions. Is there any answer to that question at the moment?
There's no definite answer. The theory that many people think that is the most likely one is that these are magnetars that found a lot of support by an observation that was done or by an event that occurred about 3 years ago. We had a very strong fast radio burst-like event from a galactic magnetar, SGR 1935 something. That was detected by 2 telescopes that were not directly looking in the direction. Estimates go that this was a pulse in the Magallansky range. And if you calculate that, that tells you that you haven't quite reached the energy levels of a extragalactic FRB, but you're getting in, let's say, in the ballpark. You're maybe only 1 order of magnitude away from the energy that fast radio bursts delivered. So this was a very strong support. Maybe if, yeah. If you do a comparison, we have done a lot of magnetar observations. So we have about many 10,000 of single pulses from a magnetar. So we know very well how do they look like. If we put a single pulse of an FRB and a magnetar side by side, you can tell the difference. They look the same. They have many characteristics which are the same. There are a couple of things which are different, though. First of all, and that's the thing that disturbs me the most about the magnetar theorem, the magnetar is a rotating object, just like a pulsar. It is actually a pulsar-like object, and it emits the pulses in its rotation period. And I mentioned that we have tens of thousands of pulses which we can detect as single pulses. And not a single one, to the best of our knowledge, not a single one has been out of phase. So they always come in the time window of the rotation. So you would expect then, if FRBs were magnetars, you would see that rotation pattern somehow. And there has been a lot of effort trying to see, are there any rotation periodicity? I think the best analysis with the largest amount of data was performed by the people that work with the FAST telescope in China. They had an observation of it within a short period of time with maybe 100 pulses or more. And they looked for periodicities, not only a straightforward periodicity, but also for binary systems or strong spin down and whatnot. They have really very carefully looked at all options that could show periodicity or would hide periodicity. And they haven't seen anything. Again, this recent FRB that was detected, which I had shown, where you have several pulses in within a minute, also no periodicity. They're sort of arbitrary in this 1 minute. And our own observation, which I mentioned, where we had 2 pulses 12 seconds apart, we also looked at what are the closest by. We had something like 200 seconds, but again, that didn't fit in any scheme. So this is something that speaks against that. Another area of difference is the FRBs tend to be bandwidth limited, much more than the magnetar. So the magnetar that we have observed always, constantly, all 10,000 essentially fill our complete bandwidth of 100 megahertz. And that's not the case for the FRBs. They sometimes only visible in part of the spectrum, and especially we have more data than from our own telescopes, where we have another L-band coverage from Torun and the others, which have a slightly different spectrum. And we do see that it is bandwidth limited and appears sometimes here, sometimes there in the spectrum. And we haven't seen that for the magnetar. So yes, there are good arguments that speak for the magnetar theory, but there are also arguments which speak against it. So I guess it's open, and we just have to do more observation, collect more data to see whether we can really refine it down.
Yeah,
that was a long answer to a short question.
Yeah. Any more questions?
Just a quick one to say, based on an amateur effort and all volunteers, to maintain that sort of observing program over such a long period is mightily impressive. Is that what the big thing you can offer into your collaboration? The number of hours you can dedicate to one particular object?
Yeah, that's one of the things that we can offer. As you can see in these programs, in the second program, we have contributed half of the overall observation time from all 4 observatories. So we can contribute a lot of observation time. Another factor certainly is that our instrument is equal in sensitivity to the other 25-meter instruments. So we are on equal footing with them.
There you go.
And yeah, that's also something. And then, of course, I think a key element is you have to win some credibility. I mean, it doesn't come from day one as an amateur that you're taken serious. But I think the time when we had our first FRB observation and issued an astronomer's telegram, from then on we were taken serious by the FRB community.
I have a question. Is there a list somewhere that you can look at that lists the various FRBs that have been observed in their locations?
Yes, the best is a website by the CHIME telescope. They have a list. If you look at the website of the CHIME, I can check what the URL is. They maintain a list. The list is not always completely up to date, because sometimes they want to wait until they have a publication out, but there's a fairly comprehensive list.
And on the astronomer's telegram, how frequently does an astronomer's telegram come out indicating that there's an FRB being heard?
Well, it's actually up to the authors how quickly they do it. Once you have formulated it, you submit it, and it immediately goes out if you have the credentials that you're permitted. They have a permission from the Astronomers Telegram organization to send it out.
Well, I'm talking about more the frequency that it's happening. Like, are you getting these notices several times a month and having to digest
Well,
them?
the idea of the Astronomers Telegram is that you notify other observatories of something that's new and which deserves attention by other telegrams. You would typically not send out, once detection is done and the first follow-up observations have confirmed it, you don't submit a astronomer's telegram for each pulse that you detect. As you can imagine, we had, in this one program, we had 190 pulses. If we would send an astronomer's telegram for each of that would be just over the top. So yeah, for new detections, for new detection of repeat FRBs, people would typically send out an astronomer's telegram inviting others to do confirmation observations, maybe to also look at other parts of the spectrum. And that's it essentially for the FRB side.
Thank you.
Is there any speculation that FRBs might be associated with luminous fast blue optical transients?
To the best of my knowledge, there has been no optical observation or no observation of an optical counterpart directly, so that there was a flare of an optical object. Of course, this has been looked for. What you do see if you go to the magnetar, you see a coincidence between a X-ray or gamma flare. Typically, you have a X-ray and gamma flare, and the radio flare comes after that. But to the best of my knowledge, there has been no correlation between any events in the optical or gamma or X-ray with fast radio bursts. I have to say that with a bit of caution, but that's to the best of my knowledge.
Andrew Thomas has very helpfully put a link for the catalogue at Chime, so that'll be in the chat. Also in the chat, we've got a couple of questions.
Okay.
The 5 burst event you were talking about, were they similar in energy?
I'm sorry, I didn't quite get the question.
Yes. Your last slide, I think, or towards the end, you showed an event that was 5 bursts that was really quite fascinating. Were those bursts of the same energy?
No, they were not exactly of the same energy. As far as I recall, they were not too much above the detection threshold. I think the lowest signal to noise ratio was something like 7. And the best one was in the 14 range, but I would have to look it up in the astronomer's telegram. But the main message is they were not of identical energy, which, by the way, is also for the fast radio bursts that we observe. They are typically can vary in the energy by, I would say, 2 orders of magnitude. We have seen our detection threshold is roughly something like 10 Jansky peak power or peak luminosity, and they can go up to a kilo Jansky, the very bright ones. So the very first that I had shown, this one was peak flux density with 200 Jansky, and the energy, the fluence, which is the sort of the integral over the pulse, was 381 Jansky milliseconds. I think the highest energy that we had measured was something like 1500 Jansky milliseconds in that range. By the way, that's also true for the magnetar pulses. They vary in energy quite significantly. So that's again a commonality between magnetar pulses and the FRBs. And by the way, that also holds true for the giant pulses from the crab pulsar. They also vary quite a bit in energy.
Again, from the questions, Stephen Berth was asking how you're funded. Can you just say a little bit about the structure of Astropeiler, because it's very unusual for an amateur organization to have such wonderful facilities.
Yeah. The funding is organized as follows. First of all, the whole premise that you see on this photograph, which I'm just showing, is owned by a foundation, the North Rhine-Westphalia Foundation, which also did the funding of the refurbishment of the instrument. And what their role now is, they're sort of our landlord, and we operate it. We don't pay any rent. However, we are responsible for all the operating expenses, which means primarily the energy cost, electricity bill and heating and all the things that are similar things. When it comes to a major repair at the building infrastructure, that is supported by the foundation still. But if it comes to any instrumentation investment and so on, that's our job. The funding comes from several sources. First of all, we have a member contribution for each member has a certain contribution. Then we have visitors that we show visitors around. There's an entrance fee for that. Then we have university lab courses, and the universities pay for that. And then we have donations that bring in money. Those, I would say, are the main sources. The overall budget or operating budget typically nowadays is about 35,000 euro per year. That's the operating cost that we have. The majority of that is energy cost.
Yeah, thanks, Wolfgang. There's some more questions come up in the chat. One is about the instrumentation, about the preamplifiers and the noise temperature.
Our noise temperature is system noise temperature is 35 Kelvin, 35, 30, 38. There's a question. Let's see what preamplifier do you use? We were very fortunate. That was, by the way, when we had this interruption when we did maintenance, we also replaced the low noise amplifiers. The noise amplifiers were donated to us by the California Institute of Technology, to be precise, by a gentleman with the name Sander Weinreb. Sander has been developing low noise amplifier for radio astronomy, I would say, for all of his life. The gentleman is in his 80s now, and he's an extremely capable person. And he has developed these preamplifiers. They have a noise temperature, the amplifier itself, of the ones that we have, 8.7 Kelvin at room temperature. That's really the big thing, that these amplifiers have such a low noise figure at ambient temperature. Typically, you achieve that only with cooled amplifiers. So we are very fortunate to have these low noise amplifiers. You can't buy them. You can only be given. So we were, the story is that I gave a presentation on a conference, and that triggered Sander to be so generous and provide us with 2 of these amplifiers.
Going back to FRBs, what have you calculated the dispersion distance for those that you've detected?
Yeah, you can do a very rough calculation. The difficulty with that is you have 3 contributions to the dispersion measure. The first one is the dispersion of your own galaxy. That's a no-brainer. You take the electron density model, and that's the piece that you know comes from our own galaxy. The trouble is with a distance is that you don't know how much of the dispersion is contributed by the host galaxy and how much by the intergalactic medium. So to differentiate between those two, it's highly speculative. Of course, you can do a very rough rule of thumb, but this is very inaccurate. The reason why we know the distance, especially for the first two FRBs that I've talked about, is that because they have been localized. There's an interferometry measurement, they have been localized to a specific galaxy, and you know the redshift of that galaxy, so that's where you have the distance. For the last one, there is a possible source, which is a cluster of galaxies where also the distance is not known to that precision. So that remains a bit open whether the 425 megaparsec is really correct. I'm hoping that we get a better localization and therefore specific galaxy once we have the interferometry measurements evaluated. Okay, I think that covers the question in the chat, right?
Yes. Any more questions from the floor, as it were? Not this evening. That's really good. Thank you again, Wolfgang. It's always good to hear what you're up to. And I think the first time you presented in this forum, I did say at some point we'll have you back in the future as the story unfolds. And I think that's still true. A couple of years' time, we'll have you back again, and we'll see you in the meantime, I'm sure, as the story unfolds. So that's great and really very interesting indeed. Thanks again from all of us here. Next.
Thank you very much for having me tonight. And my apologies that this was sort of a presentation stitched together from various things very quickly.
You did so well. Yeah, and I think we can all join Martin Kinder in a round of applause and a standing ovation for you. It was another very interesting evening. Next month we've got Whit Reeve, and just as a small comment, if you want to be kept up to date with the story of EUCARA 25, then do visit the website and tick the box, keep me informed. And somebody was asking the question, why are RAL Space involved? I wanted a local host on the Harwell campus, and they've got some people there that are very interested in radio astronomy, although that's not their key interest. And they've been enormously helpful in providing facilities, etc., for this conference. So that's why RAL Space are involved. Okay, until next time, good night, God bless, and see you again shortly. Bye-bye, folks.
Goodbye.
Thank you, Paul.